Suppose that you've got a length. Now, anytime you grab a ruler and you do a measurement, we know there's going to be some error bar at the end of that. We're going to have a little bit of uncertainty in how we're reading it each time. And we know that it's going to be a random sort of uncertainty from our readings. So we can expect that if we were to do hundreds of these readings with the ruler, we'd probably end up getting a nice Gaussian distribution, a normal curve. And what I've done here is I've actually created a normal distribution. It's just that the shading is actually the y-axis, and of course the x-axis is the length here. So you can have kind of an idea of where exactly we're saying that the end is going to be for this line. Now, if I go ahead to the format box in PowerPoint, I can specify a length. Now suppose that I wanted to have a 4-inch long object, and this was the error bar on it. We don't really know, in terms of the actual length, where exactly the end of this would have stopped if we were talking about this purely numerically instead of graphically. Now suppose that we are going to grab another piece of wood and we're going to stick that piece of wood on the end. I'm going to set it offset just a little bit so we can see it a little more easily. And we know that we're still going to have this uncertainty. The thing is, should I be sticking this point right here in the center? Or was the actual real length short or long? We don't know because there's some uncertainty. There's going to be some squishiness in this. Now, picture that we bring this in and there's going to be the blur on it. Let me give it, there we are. Then we can see the line better. These two are going to add together, but not directly. It's not going to be a linear addition on this. But they are going to contribute to some sort of an overall error bar. So the more error we have on each measurement, obviously the more cumulative error we've got, but it's not going to just be this has 2 units of error and this has 2 units of error, meaning we have 4 units of error for these two combined. It's actually going to be a little more subtle than that because sometimes this one will be a little bit long and this one will be a little bit short in the reality of it. And so we actually do see that they add, but they also help cancel each other a little bit. Now, that's a little bit hard to visualize. Luckily, there's already a set of equations that will help us in order to do those things. Now, most of our glassware that we have, and even in many of the rulers, there's actually going to be a listed uncertainty level that's common for that piece of hardware. And the nice thing about that is we can take that error that's already known and we can determine a total error from each of the component errors. And you can see that the book they gave in, and the equation they gave in the book, here I'll make this full screen so I can write, it shows it as if we were doing a total of 3 measurements, but really we can have as many measurements as we want to be adding together. If we only have 2 values, then obviously we would just use this sort of a thing, and we just use the subscripts to tell us, what one we're talking about. Instead of having E4, I'd probably call that total error or ET or something, I don't know. Just to help myself realize that this number is going to be different than these because it's the accumulation of all of those errors. It's just a helpful way to keep track of what we're actually working on. Now what we'll do is we'll take the errors and we'll square each of them. We'll add them together and then we take the square root. Now mathematically you can see that that's what I was saying a minute ago. And if I only had one error, the error value squared then square rooted would just be itself. It'd be the same value you started with. When I add them together, those numbers aren't going to be quite linearly additive. Let me prove it. Let me go ahead and just stick the number 2 in. Let's say that the error bar on both these had a value of 2. We won't worry about what the real value is and the error that it's describing. We're just going to plug this in just to see what happens. Now, if these were totally additive, we'd say that this would be 4. So I'm going to square this. That'll give me 4 plus another 4, meaning I have 8. Now I'm going to take the square root of the number 8. Okay, so let's do the square root of 8. I put in my 8. I'm going to use that. It's going to be to the root 2. Here we are. So the actual error on that should accumulate to be 2.8. So 2.8 would be the accumulation of error for 2 and 2. So you can see it's bigger than either of them, but it's not as big as the sum. That's going to be pretty standard whenever we do addition or subtraction. Because remember, subtraction is exactly the same thing. It's just that we'd be, instead of measuring our board of wood longer, we'd be measuring our original board of wood and then measuring backward with the ruler to decide where we're going to take our saw or whatever we're doing. That's the kind of thing we're talking about when we talk about these errors. So if we're talking about propagation of uncertainty for addition or subtraction, that's the rule that we use. Now let's change things up a little bit. Suppose that instead we were going to have a case where we're going to be multiplying these together. So let's say that we took two lengths. Both of these lengths have a random error associated with them. And we're trying to figure out the area of this box. There we are, just to help visualize what we're talking about. Now, we don't know how much error is going to be right here. We don't know how much error is right here. But we can picture that sometimes both of them are going to be on the big side, and we're going to have a bigger area. Sometimes both are going to be on the small side, and we're going to have a smaller area. And what ends up happening is that as we accumulate multiplied errors, most of the time what we're going to see is that they end up helping to offset each other a little bit. And so we'll actually see a reduction in error. So averaging is going to actually really help us in trying to reduce error, because that's effectively what we're going to be doing, is pulling lots of these values together and reducing them down. So the multiplication really helps in this. Now, we'll talk more about real averaging later on. I'm talking about just the broad concept of averaging. Real averaging we'll see when we talk about things like signal averaging. But right now, I'm speaking crudely. Okay, so we see our area here. Now, let's actually get the equation up there just so we can see how we handle it when we're multiplying things together. So you can see here the equation. We're going to have the percent error. Notice that means we're going to take the error, so the standard deviation that we had, divided by the average that it's describing. Times 100 gives us the percentage. We put in the percent error, we square it. We do that for everything. And so sometimes you'll see a different equation. You know, if you just grab a book and you're looking for it, or you don't have your book handy and you look on, Google, you may find instead that they actually have expanded that to say standard deviation divided by average times 100. Well, that's exactly what we're talking about. So definitely try the sample problem that you'll see on page 58, just to see an example of multiplication and division. What you're going to find is that we have to talk both about the percent error and the actual error. So we have to convert relative uncertainty back into absolute uncertainty. Because as you see here, we convert absolute into percentage. We determine a percent error. We have to convert that back to absolute. So you'll have your average or your multiplication problem or whatever you're doing. These are the errors that are associated with all those values. You'll have multiplied your two real values together to get your final answer. You'll then take these errors, put it in here. That'll give you the percent error on that average. And then you still have to find the absolute error. Now, if we have multiple operations, we use our order of operations and we do each of those separately until we finally work our way through the entire problem. So if there's a lot of different components of it, that can take a little while. Now, this does get to a really important idea, though. When you do propagation of error, I want to remind you of something in a previous video. I said that we use sig figs to describe what's going on for one value. But when we have multiple values, we actually start to have statistics. And statistics, at least the kind that we use, is mostly based off of normal distributions, Gaussian curves, those sort of things. Now, what we see from this is that we actually do get an error bar. Now suppose that after going through my calculation of error, I pull up a pen, suppose that I found that my final answer was going to be 24.01 plus or minus 0.14. What this is communicating, better than sig figs and using sig figs ever would, is that this is the value where we start to have uncertainty, which means that this is the last known value and this is completely unknown. And so the proper way to write that would have been 24.0 plus or minus 0.1. Now this is also where in the book you'll find that drop notation that we use for a dropped figure at the end, because sometimes this just looks a little bit too crude to give people as refined of an idea of where the error bar really is. And so what people will sometimes do is they'll write 24.01 plus or minus 0.14. That's really good to do because it allows you to keep that extra sig fig when you're doing subsequent calculations, and it also helps communicate to the viewer exactly how unknown that last known place is. So that's a very common piece of notation that you'll see throughout the textbook, and it's really useful to use when we get to things like our periodic table. We often think of the periodic table as being something that we know incredibly well, but remember, every atom on that table we had to discover and then do measurements for. And each of those have different isotopic distributions, and depending on their source and nature, they may have a totally different set of isotopes present that are naturally occurring and stable and different ratios. Which means that different sources can have different molecular masses. And the sig figs that we see on the periodic table, especially when they actually do show an error bar on those masses, well, that lets us know how well that's known. We should be using those errors and propagating them in whenever we are doing a molecular mass calculation. Now, that said, the good news is that we have so many more figures posted on a good quality periodic table, like the one you'll find in your analytical textbook's front cover. Those have so many extra sig figs that we're unlikely to actually need them when we're doing our calculations for most experimental work we do in the lab. So very rarely do we actually have to do a full error propagation for molecular masses. But you can see a couple on the periodic table, if you're looking at it right now, where we're going to have a bit more uncertainty and we might have to start caring about it sooner. Things like germanium, where there's only 4 sig figs and the error is in that 4th place. Or, let's see, there's a couple of other short ones. Bromine, krypton, and argon only have a total of 5 places in their entire figure. Germanium has 4, gallium has 5, copper's only got 5, zinc has 5. You know, there's quite a few on there that are going to have fewer sig figs. Lead only has 4 sig figs because it has a lot of different isotopes at play. And that gets brought up in some of our analytical work that we'll talk about later on. And knowing exactly what the source is can sometimes refine that number further once again. But keep those things in mind. We always need to be using uncertainty whenever we do these calculations. Definitely look through the uncertainty and molecular mass information that's on page 63 of the 8th edition of our textbook. It also talks about things like multiple deliveries from one pipette. That would be an accumulation of additive errors. So we'd follow our addition-subtraction rule. Okay, so I just wanted to highlight our error propagation rules.